Okay, we can get started. Thank you. I want to welcome everybody to a new semester and to the Colloquium, to the Distinguished Colloquium series for this semester, which we kick off with Mike Landry. I'm very privileged to introduce Mike. He received his PhD from the University of Manitoba, where he worked on strange hadronic physics at like UBC and Triumph and Brookhaven, and then went on in 2000 to do a postdoc at Caltech and to start working on LIGO. And he's kind of been there ever since, transitioning from, upward from one job to another and more responsibilities. And now he finds himself director of the observatory at Hanford, which he's been since 2016. And I'm really pleased that he was able to join us today and give us some overview and some perspective and some fun stuff having to do with gravity waves. And so, Michael, thank you so much for coming.
Great, thank you very much. Thank you, Brian. And thank you to WSU for the opportunity to come talk to you about gravitational waves and tell you about LIGO. Just before we start, that incredibly hypnotic set of simulations from these 10 binary black hole mergers were made by Matt Dewey and the SXS collaboration using LIGO and Virgo data. So just check it out on YouTube if you want to see that. It's great, just great. So if you haven't actually been to LIGO Hanford Observatory, please let me invite you to come out. We'd be happy to give you a tour, tell you all about the science, the lab, take you around. So just let us know, let myself know, or let Amber Strunk know, our EPO outreach coordinator know, and we can get groups of students in. Any groups you bring down, we'd be happy to. It's just 2.5 hours south of here. So I had a great day meeting people, and especially meeting the students at noon, students and postdocs at noon. So please do come down. I'm going to tell you today a status of LIGO. I'm going to be setting this in context of this new paper that's come out in December, which is Gravitational Wave Catalog #1, Transient Catalog #1. And really that's about their first 2 observing runs that we had. LIGO and Virgo held 2 observing runs, one 4 months long, one 9 months long, 01 and 02 we call them. And upon review, we have 4 new detections in binary black hole detections in the data that were just announced in December. So I'll give a little introduction on the instrument, something on the observing runs, talk about the early detections, and then I'll cover some material on this. And then lastly, I'll close with some material on future detectors, the next observation run that's coming up, the upgrades that we propose to this instrument, and finally 3rd generation detectors. So before I start in on that, though, I just have to mention what gravitational waves are. You probably know these were predicted by Einstein in 1916 and first detected in 2015. They're distortions in the metric of space-time. So if you have some flat Minkowski space, these are envisioned as perturbations on that flat space due to the acceleration, quadrupolar acceleration of dense matter. Matter moving at the speed of light and massive components should give off shutters in space-time that propagate out from the source and be detectable by the terrestrial-based detectors. They're expected to follow at the speed of light. We'll see we have a measurement of that now, a direct measurement, and come in 2 polarizations. The thing is, they're really weak. They're hard to detect. And that is shown in this approximation. Gravitational wave strain, the change in a length divided by the length of the system. So you can imagine engineering strain in a meter of steel or something. If you heat it, the delta L can be some tiny change, fraction of a millimeter, and yield a strain of 10 to the minus 3 or 10 to the minus 4 and that. Gravitational wave strains, it turns out, are down at the level of 10 to the minus 21 to 10 to the minus 24. They're really tiny. And that is shown by this 1 over r, the distance from the source to the detector. That's punishingly small. And so is this c to the 4th term. So that yields these really tiny strains in space. Thing is, they don't interact with matter much. They're tiny, so they're hard to detect But that also means that they're an excellent probe of dark sectors. They're a way of finding out what's going on at the cores of supernovas, or that there's a field of heavy stellar mass black holes in the universe merging into larger black holes. So it allows you to probe aspects of the universe that are dark.
Sorry to ask a question.
Yeah, no.
Why would it go as 1 over r instead of 1 over r squared?
Well, it's a strain, right? Energy is still propagated. Yeah, energy is still propagated and falls like 1 over r squared through some shell that's expanding out of the source. But the gravitational wave strain falls like 1 over r. And furthermore, that means it's sensitive to the length of your detector. So the reason why we have 4-kilometer long arms is, one, because we have a really good funding agency and can afford to build a vacuum envelope that big, but two, that the strength of the signal goes, delta L goes as H times L, right? Okay, so what are the sources of astrophysical sources that should give off gravitational waves in the audio band? The sources we're looking for modulate space-time at tens of hertz up to several kilohertz. That just so happens to be in the audio band. You can actually hear the waveforms if we play them. We have seen these compact binary coalescences. About half the stars you see in the night sky are pairs of stars. They're just so far you can't see that. So we know of binary neutron stars in our galaxy. People theorize there may be binary black holes. And indeed, that's what we have seen, the merger of these two systems as they revolve around each other for no one knows, tens of millions of years, billions of years, giving off weak gravitational waves, finally merging to form a larger black hole. And so black holes, two neutron stars, one of each. We've seen the former two. We haven't seen this black hole neutron star event yet. But those are the sorts of compact binary systems that we're looking for. Then these three, we haven't seen these types of gravitational wave emitters, but we expect that core collapse supernova may be a burst source, cosmic strings. They may be sources of burst-type gravitational waves for which you don't have a nice model the way we do in compact binary coalescences. So this is a hard search to do because you're looking for something you don't know what it is, coincident in both detectors. Spinning neutron stars in our galaxies, if they have some mountain or R mode or precession, you should give a weak but continuous gravitational wave signal that you can tease out of the data by integrating over time. And a gravitational wave background, that could be something analogous to the cosmic microwave background, a stochastic gravitational wave background from the early universe, or it may be the sum of all binary black holes in the observable universe that give off this background popcorn source. And then something unexpected. We genuinely could get a surprise. That's happened in other fields. In radio astronomy, we have FRBs, we had pulsars in 1967. You could get a surprise where you have some sort of unmodeled source of gravitational waves, and that's really exciting. So our detectors, our funding agency is the National Science Foundation. It's currently shuttered, of course, because of the shutdown. We can't talk to our program officer, but the NSF is indeed paid for most of the gravitational wave research in North America. And it includes 2 observatory sites, one in Hanford, Washington, it's near Richland, and the other is in Louisiana, LIGO Livingston. And the pair of 4-kilometer L-shaped detectors, which house a 10,000 cubic meter vacuum envelope at 10 to the minus 9 torr. That's what comprises each of the observatory sites. And they operate in tandem. So you're looking for gravitational waves passing through the Earth, coming from some distant source, modulating the relative arm lengths in a way that can be matched up coherently at the 2 sites. We ran initial LIGO from 2000 to 2010, and then we shut down for 4 years and pulled all the guts of the interferometer out of the vacuum envelope and installed new components, so-called advanced LIGO, with the target of being 10 times more sensitive broadband. We turned on in 2015 with our first observing run, and I'll tell you about the first detection. So what's so advanced about advanced LIGO? First off, well, everything. You can't just improve on certain aspects of the the frequency band, the sensitive band to the detectors, you have to push on everything. So at low frequencies, you better isolate the optics with a series of pendula and tables that decouple the mirrors from the ground. We don't want to be a good seismometer. We don't want to register the motion of the ground. We want the optic to be very still so that you can sense the differential motion induced by the passage of a gravitational wave. The arms themselves have, well, one, you inject a high-power laser, infrared laser, into arm cavities that have a power that builds. At 200 watts of operation, you build to nearly a megawatt of power in the arms. And you read that out through DC photodiodes. So in vacuum photodiodes, wavering voltage as a function in time, that encodes the astrophysics at the source. So the arms are modulating, and you read those waving arms out on these photodiodes, and that encodes the astrophysics. Of course, it also encodes trucks driving by on the 240 highway, earthquakes, tides, everything. So you have to know about your environment that the detector lives in. The optical configuration is not just a simple Michelson. So it's this power and signal recycled interferometer with Fabry Pro arms. So you take laser light and inject it onto a beam splitter, which sends half the light into one arm and half the light in the other. The light combines, and we hold the output port on a nominal dark fringe. It's not truly dark. We leak a little light through to generate error signals to close loops on the differential arms and other degrees of freedom, but primarily that. So we're leaking a little light through here, and we then build power in the arms. This is a partially transmitting mirror here, so that you build up at design sensitivity to about 800 kilowatts. On entrance into the interferometer, you first go through a transmissive mode cleaner. So this triangular configuration round trip is about 32 meters. And the light rattles around in here before the lowest order TEM00 mode of the laser is transmitted. Higher order modes are rejected. About 95% of the power is in TEM00. That's transmitted into the power recycling cavity. So if this is a Fabry Perot cavity on which you resonate light, if you hold this arm length at an integral number of half wavelengths, all the power couples in. It's just a transmitter of 1.4%, but all the power couples in when you hold it on resonance, and power builds. If you imagine this power recycling mirror as one mirror and everybody else as a compound mirror downstream of it, you can generate another coupled cavity, this so-called power recycling cavity. On resonance, most of the laser light's being sent back towards the laser. You want to use that to reduce the shot noise, so you couple it back in with another partially transmitting mirror. We play the same game on the output. This is the signal recycling mirror to tune the response of the interferometer and couple light back in, couple signal back in, and then finally read it out on these DC photodiodes, which are passing through yet another mode cleaner. Yeah?
If I remember right, Michael one had a 50,000 watt laser at the front end, but then that got mode cleaned and frequency stabilized down to about 5 watts. What's the new configuration?
So it was the old configuration initial LIGO was a 10-watt laser, max, injected onto the interferometer. And so by the time you pass your mode cleaner and scatter light out of the optics, you might have had something on the order of 7 watts injected into the interferometer. We moved to a medium power stage, advanced LIGO in S6, 35 watts, and then finally we built advanced LIGO, so this exploited that 35-watt laser, and we have the 200-watt high-power stage. And it's a little more complicated than that, but I'll get to that in a slide or so. Yeah?
In regards to this diagram, is there a feedback loop where you lock onto the fringe?
Yeah, in fact,
Can you talk about how you do that?
I'm not going to give much detail on it, but there's more than 300 high-frequency control loops, 16 kilohertz sampled control signals. So a multi-input, multi-output control process of suppressing motions in the interferometer. So you have the primary one is the differential length of the main interferometer. And we generate the error signal at the output photodiode and feed that back to the end test masses. So even though you're getting a signal, you stamp it out.
So that's what I'm interested in, is what are the feedback transducers? How do you couple?
You couple those through electrostatic oscillators and electromagnetic oscillators all the way up the chain. I'll point those out to you on a coming slide. So if we're trying to distill to two things what you have to do to make an interferometer, gravitational wave interferometer work, it would sort of be like this. You have to do two things. You have to make your mirrors very still, and you have to make your laser light very pure in order to sample where they are and what their relative motions are. So a lot of expenditure, effort, time, and capital goes into this. So let's take the mirrors first. If you look at the ground motion at Hanford, you measure that with a good seismometer, it's about 10 to the minus 9 meters per root hertz at 10 hertz. You're trying to make a differential motion, a displacement motion at the level of 10 to the minus 19 meters, which is the design sensitivity. So that's not in strain. We haven't divided out by 4 kilometers yet. 10 to the minus 19 meters. We have a factor of 10 billion to go. So the surface of the mirror that is in the interferometer has to be a factor of 10 billion quieter than the ground motion below it. And so we have to do a lot of decoupling. So we suspend these optics as pendula. So this fused silica optic, which is 32 centimeters across, 20 centimeters thick, is suspended by glass fibers, CO2 laser welded glass fibers, to another penultimate mirror, which is not an interferometer mirror, but the whole thing becomes a monolithic structure, 40 kilograms, very low thermal noise. That's the motivation, is to reduce thermal noise in the interferometer. And that gets suspended by wires to a table, which is suspended to another table, which is suspended to another table, which is suspended to another table, and finally a table. And then that entire 12,000-pound payload for one test mass in the arms is then goes in the vacuum envelope, and these support tubes pierce the vacuum through bellows. So we've taken out the chamber here so you can see the system. And the entire payload can be actuated through hydraulics. And that's because there's not just low frequencies to actuate on at each one of these. So this is actuated electrostatically by a neighboring optic. These are actuated electromagnetically with coils and magnets. And that whole chain progresses all the way up with electromagnetic actuation throughout. You feed back for ground-based seismometers, feed forward for ground-based seismometers. The tides, the lunar and solar tides, transport the end stations to or from the corner station by plus or minus 100 microns every 12 hours. That would rip you out of lock in seconds when you're resonating light in the arms. And so the hydraulic systems oppose the tides. If there are storms off the Aleutian Islands in Alaska, or off the coast of Labrador, or off the Gulf of Mexico, that beats against the continental shelf, and so that puts an undulation with a period of 7 seconds, the so-called microseism, into the ground. So in times right now, sort of November to February, when storms are high, a lot of work is done at low frequencies to oppose the microseism. So all of those things, all the way up to bandwidths of 300 hertz or so, you have to suppress motions of the optics. And here's one of the systems in situ. So that's one thing you have to do. And then secondly, you have to make pure color lasers to probe that. So we have a neodymium YAG system, 1064 nanometer infrared laser, which has these stages we discussed: the low power stage, 750 milliwatts, medium power stage, 35 watts, and high power stage, 200 watts. And they're stabilized. They're ultra stabilized in frequency, amplitude, and mode. And all of that is in order to have the right characteristic to send it into the interferometer and not induce sensing noise into the interferometer. There's a host of different subsystems. I seem to have lost a picture here. I don't know why. There's a host of different subsystems which I can't discuss. If you're sending light through mirrors, the neighboring mirror here in the input test mass stage, then you induce a thermal lens, and so you have to correct that thermal lens with annuli of CO2 laser light on the optic to make uniform heating. You use ring heaters to compensate. There's green laser light systems, which are auxiliary lasers, which allow you to control the interferometer and cause it to lock and resonate. And there's readout electronics, there's telescopes and systems. So there's a host of different systems, yeah.
Can I start the line width of the laser?
Sorry, can you say?
The line width of the laser.
Yeah, 10 millihertz or so.
Okay, so
Yeah.
coherence length and
I haven't got the coherence on the top of my head. 10 millihertz on the line width, though. Yeah. Finesse of optical cavity finesse of 350 or so. Okay, so once you build these two interferometers, one at Livingston, one at Hanford, we would then go and do commissioning experiments to reduce the noise. So here's the noise. This is the readout of the photodetectors at the output of the interferometer. So you're trying to sense differential motion. That's a wavering voltage on your photodiodes. And if you take those data and cast them in the frequency domain and then calibrate them, you need some absolute length scale, and we can talk about that if you want. But you have to know if you're sensitive to 10 to the minus 19 meters or 10 to the minus 10 meters. But that allows you to take your readout of the interferometer, calibrate it in terms of strain, divide out the length of the arm as a function of frequency, and you get these characteristic bucket-shaped plots. Lower's better here. The whole game, if you come to the site, you'll find tonight there's going to be a dozen people just trying to lower the noise in the interferometer. This is read out from 10 hertz all the way up to 7 kilohertz here. And this was the best performance in initial LIGO. So this is a curve we took in 2010. Then we shut down, created advanced LIGO, and commissioned it for about 8 months and got to this in September 2015. And you can, for comparison, you don't just have to work with the noise curve. You can say, what does that correspond to as a reach into space for some standard candle? Clearly, if a gravitational wave source is louder, we're going to see it farther. So we need some sort of standard candle. The candle we use is 2 neutron stars revolving in and merging. Signal and noise of 8, angle averaged over all sky, all directions. And this computed to 20 megaparsecs. So really, that was the initial LIGO high water mark, 20 megaparsecs. The goal for advanced LIGO is about 175 megaparsecs. That's where we're trying to get to. In something like 8 short months, we got to about 70 megaparsecs. And we're essentially ready to make our first observation run. So that's what these strain curves from, one from Hanford in red, one from Livingston in blue, computed to. And at that time, we were thinking we would run a series of observation runs interleaved with commissioning to improve the noise on the interferometer. And we wanted to be at the 60 to 80 megaparsec range for the first observation run, and 60 to 100, and a target for 120 or greater for 03, our third observation run. And it turns out that Virgo joined on in the second observation run at reduced sensitivity. So here's a couple of plots. Here's those noise curves again. These are from 02. This is actually the second observation run. Blue in Livingston, better performance at low frequencies. I can tell you why that is later if you like. Red in Hanford. The reach into space, 80 megaparsecs Hanford, up to 100 megaparsecs at the end. We had an earthquake at Hanford that charged an optic and took us offline, brought us down to 60, 70 megaparsecs there. And the durations of the run, September 12th to January 19th, 2015 to 2016, the first observation run, so roughly 4 months. The second observation run from late 2016 to August 2017, remember that month. That meant you had about 160 days, 66 days of coincident analysis time. The big deal for this catalog paper that was released in December is that we recalibrated the data, did some noise corrections for beam jitter in the interferometer at Hanford, which is one of the reasons why this has issues at low frequencies, and modified source codes for searches, and that proved to be important.
How many galaxies lie within that?
Oh, good question. Yeah, yeah, I did know that. It's sort of on the order of, roughly 10,000 in the first case and 100,000 in the second case, something on that for binary neutron stars. But I'm taking a wag at that. I could find those for you. All right, so yeah, after we commissioned the detectors, we got our first detection. Actually, it was on a Monday morning, and on the Thursday prior, we were supposed to start the run on Monday morning, and we elected to say we'll delay it to the following Friday because we weren't quite ready to tell astronomers, yeah, go look in this direction in the sky. But at 6:40 in the morning or so on Monday, Nature started the run anyhow. And this is the event we got. So it's binary black hole merger, time series from Washington shown here, time series from Livingston shown here, and the time frequency plots there. And these were the first 3 observations that we made. This is the first one. This is the Christmas Day, so-called Boxing Day event here, much lighter. But they're heavy stellar mass black hole binaries, merging to objects as much as 62, 63 times the mass of the sun. This was a trigger, sort of low noise trigger. We called it LIGO-Virgo trigger. The date structure here is the year, month, day, so LVT 15, 10, 12. We discovered that offline. We discovered these 2 online in the first observation run. And these 3 came from our analysis, our first pass of the analysis in the second observation run. It's really these 3 events for which Barry Barish, Kip Thorne, and Ray Weiss won the Nobel Prize in Physics in 2017. So one of the big deals in the second observation run is that we added a detector, and that turns out to be important and fortuitous. So here's the 2 LIGO detectors that we ran in 01. We ran 9 months, 8 months on our own, and then in the last month of August 2017, Virgo joined on. We expect Kagra to join on in 03, the third observation run, and 2025 LIGO India to come on board. So the current network is these 3 detectors as used in the 02 observation run. August, 1 month prior to the end of the run, kind of the word on the street was, we probably won't get any binary black hole in that time, and it was 2 weeks before Virgo had their first detection. Yeah?
I was just wondering if the other detectors are all fairly identical, like same arm length? Or?
Yeah, good question. So this is a very, every instantiation is different at Virgo, but it's basically the same design, okay? The same general Fabry-Perot arms, fully dual recycled. This is the 3-kilometer detector, so it has 75% the overall sensitivity for the same displacement noise. And Kagra is a 3-kilometer detector, but it's a really ambitious detector. It's in a mountain to avoid Rayleigh waves from earthquakes and gravitational gradient noise. It's cryogenic. It has sapphire mirrors. It's a very, very different setup, so it's a really ambitious project. But otherwise, they're largely the same. And LIGO India is going to be a clone of LIGO Hanford, LIGO Livingston. So you have this 3 interferometer detector. The big deal with that is that you triangulate with a smaller error box for a source. So here's the error box that forms with 2 LIGO interferometers, about 1,000 square degrees. And if you fold in Virgo in the analysis, you get about 60 square degrees. So that's already a much smaller error box to send electromagnetic astronomers at that potential source. We've done that with all of our binary black hole mergers. No one has convincingly followed up and seen a transient from a binary black hole merger. However, if you had matter in the system, like in the merger of 2 neutron stars, then you're likely to get an electromagnetic counterpart, and you should be able to see it then in gravitational waves, visible and infrared, radio, gamma rays, X-rays, and potentially even neutrinos. Going into the 01 and 02 runs, well, really in the 02 run in this case, we had MOUs written with 95 different groups from the electromagnetic and neutrino communities for follow-up. And that was because we're a speculative search. We're not sure if we're going to find binary neutron stars. We're asking them to use their target of opportunity time to follow up transients, which may be noise. These are nascent interferometers. The noise characteristics are somewhat, they're non-Gaussian and non-stationary. And so we had a private GCN alert system. So we alerted, that's what we were doing in 02, was letting people know if we had triggers. In 03, everything's open. So we've gone through that phase. We're now in an open public alert phase for the third observation run. And indeed, this is what happened on August 17th. We got a 100-second long chirp signal in our interferometer. Signal that long immediately tells you it's light on it's probably neutron stars. We also had a GCN sitting there when we got on this call that we're alerted on our cell phones that we have a trigger. And you had a Fermi, NASA-based Fermi space-based detector with a gamma ray burst indicated 1.7 seconds after the merger time. So already that is clear that you have a temporal coincidence, and there was a spatial coincidence as well. So that was a really important call. And then we made a sky map. Here's the sky map, just 32 square degrees when you fold in data from LIGO and Virgo. And we handed that off to all of our partners. And in Chile, 6 observatories found the optical transient within 1 hour. And the first to it was the 1M2H collaboration using the SWOPE telescope. So this is a DLT-40 image of NGC 4993, 21 days prior to the merger. And this is the SWOPE image 11 hours after the merger. You had to wait for the Earth to rotate. Neither Australia nor South Africa had telescopes in a favorable position given the location in the sky and given the weather patterns. So Chile was the first set of observatories that really had a chance to see it. And it took them 15 minutes. They did a targeted search on galaxies based on their expectation that neutron stars lived in these older elliptical galaxies and got it immediately.
That's, of course, amazing. Have these events been seen by the electromagnetic observatories before?
Great question. Okay, so this event was followed up by and seen in all of these different wavelengths. So each one of these ticks are GCN. That's this event. So since that time, one interesting thing is this is a very weak gamma ray burst. Okay, so it's nothing that people would follow up on, right? The Fermi sky location is 1,000 square degrees. So people aren't going to follow up on 1,000 square degrees, especially for a weaker GRB. So people have done a lit search, and there's a paper from, I think, last October, between October and December, by Troja et al. And they find a gamma ray burst which has an optical counterpart which behaves like a kilonova, reddening from blue to red quickly. It doesn't have the gamma ray signal to it. It's also at cosmological distances. We would have never seen it in gravitational waves. It would have been too weak. So there's at least one other object that really behaves like one of these binary neutron star merger / kilonova events. We will see more in the next observation run. And the case, we think, will harden for this being a source of production of heavy elements like the lanthanized golds and platinum and other heavy elements. So that's to be resolved, I think. So what else came out of this binary neutron star event? Given a waveform assessment of the tidal deformability of the system, you can then go and back out, given neutron star assumptions, the assumption that these behave like galactic neutron stars, you can go find out and probe the mass and the radius and the equation of state. And so we find, there's 2 different assumptions that are being made here in this PRL from December. Showing that the masses are on the order of 1.5 solar masses, and the radii are somewhere between 10.3 and 13.5 kilometers. So, and to exclude some equation of states allows others. So there's a lot of material here to digest on neutron stars, and you can find it in this paper, for example. Other things being learned, the first event was used as a standard candle to measure the Hubble constant, so the expansion of the universe, now not using electromagnetic waves, but using gravitational waves. That will become statistically more and more accurate as we find more BNS events. There was a direct measurement of the speed of gravity based on the arrival time over 130 million light years of the light and the gravitational waves within 1.7 seconds. And that gives them the same VC and VG to the same of 1 part in 10 to the 15. And we've begun to look at these mechanisms for short hard bursts and gamma ray bursts and kilonova. So I'm running out of time. I'm going to touch on this gravitational wave catalog and then show you some slides on the future detectors. This catalog paper was put out in December. You can get it at our website, or you can get it on arXiv, and it's been submitted to PRX. We have 4 confident new detections of binary black hole mergers. That's kind of the biggest takeaway. So this is now scanning the data in a second pass with more refined codes and data that have been cleaned at some level of beam jitter in the Hanford detector and shown in sort of this light color, light pink color, are these additional events, 0729, 0809, 0818, and 23. And the network SNR for various search codes is shown here. One of the things to note is that that initial trigger from 01, the thing we called LVT, because the SNR was so low, we weren't making a 5 sigma detection, has been elevated to a GW 151012 event. So we've eliminated the LVT moniker, and maybe we just won't use that anymore. So that event now has SNRs of 9 and 10 in our searches for templated searches for gravitational waves. Parameter estimation results, 170729, July 29th event, is now the highest mass event. So it knocks off the original event as the highest mass gravitational wave event, 50 solar masses, 34 solar masses. Those are the constituent masses, the 80 solar mass total. That's because of the probabilities associated with these. And about 5 solar masses were converted in less than a quarter second into gravitational wave energy. So that would make it the most powerful event, astrophysical event known. And all going out into the deformations that shape the space. And that is at about nearly 3 gigaparsecs away, 2.75 gigaparsecs. One interesting thing, if you plot the masses of these objects, here's the neutron star event, and here are all those binary black hole mergers. The mass of the compact objects, black with error bars, are the constituent masses. Red are the remnant masses. The binary neutron star, here's their event. We don't know the remnant mass. That coalescence is chirping up at high frequencies where the shot noise is high, so we actually have less ability to see, so we don't have anything on the coalescence there. But you can see there's sort of 2 roughly open spaces here, and then maybe above these masses. And here, this is not a LIGO paper. This is from Spira and Mappelli, a 2017 paper. As a function of zero-age mean sequence stars, what are the potential mass of black holes, compact objects, that are produced from supernovas? And here you have this band here where you don't find objects and you don't find objects here. They call these mass gaps. So there's a mass gap between sort of neutron star masses and black hole masses, sort of something like 2 to 5 solar masses. And then there's another one above 45. And if you squint, there's some evidence here for that, some support for that. I don't think it's super strong yet. But again, as statistics fill in this plot, we'll see if we really do see a sort of mass gap here. This isn't not a hard cutoff either. It's not expected to be a hard cutoff. You expect some events above, some compact objects above 45 solar masses. Okay, so where are we going next? We're starting our 3rd observation run as of April 1. We just came out of ER13, our engineering run, as we work on the interferometers to make them more sensitive, driving towards a coincident run with Hanford, Livingston, and Virgo. That will be 1 calendar year long. We're not sure if we'll make that April start date. It's always complicated when you're pushing on the noise of the detector. We may have some minimal delay, but we'll see where we get to at the end of this month, and then sort of make a decision and inform our electromagnetic friends about what our overall calendar is like. In order to make progress on the detector, here's those noise curves of the interferometer. Here's the Livingston noise curve as a function of frequency. This is cast in displacement, so we haven't divided out the arm length. You have to push on the right noise, right? So you want to know what are the components of that noise. That's called a noise budget. So you make experiments, so you push on things, you measure different photodiodes, you calibrate, some you use theoretical dead reckoning, and you get a specific noise term, things like frequency noise or seismic noise or coding Brownian noise, and add them in quadrature. So here's the real noise in the interferometer. The solid green is the summed quadrature of all the noise components, and it does a pretty good job of telling you you're limited by shot noise at high frequencies. Not a surprise. At low frequencies, we're actually uncertain. We have a gap, we have excess noise at low frequencies, so there's some mystery noise here. And that's often the case on a working interferometer, particularly at low frequencies. You don't necessarily know all the constituent noises. This could be something like charging noise on an optic, it could be scattered light noise, it could be some thermal component in the suspensions that we don't understand, but there's some component there that we've got to beat down if we're going to get to design sensitivity below 50 hertz. Same deal at at Hanford. This is our more recent noise budget. All of these constituent noises. You basically isolate the ones that you know you have to work on. It doesn't do any good to work on, I don't know, like suspension thermal noise here, or this is output jitter here, right? This pink one here. You don't want to work on output jitter when you know, this mystery noise and shot noise and radiation pressure are all bigger than that. Okay, so we've worked on many of these components. I'm just going to have to skip over these. I don't really have time. But between 02 and 03, we went into each chamber for about 8 months. And that's in order to, you know, introduce corrections to optics, corrections to scattered light, all in order to reduce the noise and improve the sensitivity in the interferometer. So you're putting in things like baffles to mitigate scattered light, new and better coatings on optics, so new optics in order to avoid, again, coherent scattered light down the arms. We replaced control mirrors with annular versions. So even though it's at 10 to the minus 9 torr, if you have molecules bouncing around between neighboring optics, then that induces length noise in the interferometer. So we carved out annular versions of those optics. We suppress optic body modes that are kicked up by higher order modes in the laser. All of these components are intended to improve the sensitivity of the detector. And I'm going to skip squeezing, and people can ask about that if they want. We register 250,000 channels per interferometer, and 30,000 of those channels are about the environment. What's the environment the detector lives in? You know, what's this? There's seismometers, wind speed meters, voltage meters, RF monitors, magnetometers, tilt meters, wind speed thermometers, anything you can think of. There's cosmic ray detectors, lightning and magnetometers. Anything that couples in the interferometer, you want to know it, you want to measure its transfer function, you want to simulate it, you want to understand, could we be fooled by some external disturbance that couples in and has a signature that's coincident in time, either because of statistics or because it truly couples in at light speed between the two detectors. And one was Ravens. They didn't couple in at light speed, but you make 10 to the minus 9 torr by using a coal trap, liquid nitrogen trap. So we have 40-foot towers of liquid nitrogen, and that's sent in to make into a torus into the vacuum envelope at each entrance into the beam tube, and molecules bouncing down the beam tube stick and freeze. And the Ravens would get thirsty and tap on the ice. And so we had microphones to identify ravens. Graduate students took out simulated raven beaks and tapped on the ice in order to make this identification, which I thought was pretty cool. That's not the only kind of environmental disturbance we get, but it's an interesting one. Okay, last 2 minutes. Let me just say we have plans for future detectors. The first is to just upgrade in a minimal way the existing interferometer. So I didn't have a chance to talk about squeezed vacuum states being injected in the interferometer, but we would do frequency-dependent squeezing and improved optics. In particular, the coating noise of the interferometer, the coating noise of the optics is the key thermal noise contribution in band at about 100 hertz. And so we want to improve those to get a factor of 1.7. So that's an upgrade that's already funded by the NSF. And we'll do that in the coming, post-04. Yeah.
When you say coding noise, do you mean noise from just the motion of the molecule?
Yeah, in the optic itself. That's right. The thermal noise of the coating itself. Thermal noise in the interferometer comprises both the core optic itself and the suspension system and everything that holds up the optic. But when you look at those terms, other than the resonant frequency of the violin mode of the fibers, you have optics suspended by a fiber, and so they wave at a fundamental violin mode. That's 511 hertz. And so this plot here, yeah, that's the forest of violins at 511 hertz there. So other than that, the coating thermal noise is the primary source. Okay, then a second upgrade with a time frame of more like 5 to 10 years is LIGO Voyager, in which, like advanced LIGO, where we pulled everything out of the vacuum envelope and put it in a new detector, we would do that trick again. So that exploits this capital cost in the beam tubes and the sites and everything. And so we would put an entirely new detector, needs R&D because it's silicon test masses, cryogenic operation. The silicon test masses require new laser wavelengths. So that gets you another additional factor of 2 in sensitivity. And you might say, factor of 2, is that really worth it? Well, if you lower the noise by a factor of 2, for a putative source, your reach improves by a factor of 2, and the volume goes as the cube of that. So you get an 8-fold increase in the rate of detections. And then lastly, both in Europe and in the US, we have designs for third-generation detectors. There's a conceptual design that's already been done in Europe for a really ambitious triangular detector, 6 interferometers at 3 different vertices. So each pair is a xylophone, a high frequency and a low frequency detector. That's called Einstein telescope. They could get 10 to the 5th binary coalescences per year. Really quite extraordinary. And Cosmic Explorer is a Voyager-like detector in a 40-kilometer long vacuum envelope. And that is a US-based design study has been funded by the NSF, and that's just starting. Okay, this has been, I'm representing LIGO and Virgo here. This is the LIGO scientific collaboration, and somewhere in there WSU is. I'm sorry, I should have looked at that before I brought the slide up. No, it's at the top. Oh yeah, there we are. And 1,200 members now, 100 institutions, 18 countries. But it doesn't feel like 1,200. It feels like 100. So here's a summary on the catalog. I think the only things I didn't say that's in the summary, this corresponds to about a gravitational wave detection about every 15 days of data search. We have rate estimates that have been now modified. The binary black hole merger rate is about 10 to 100 events per cubic gigaparsec per year. And the BNS is more uncertain. We only have the one event, but you can do some Poisson statistics and come up with this larger and very uncertain rate. So I'll close here and just note that the rates of detection for the 003 run, if we make the 120 megaparsecs at both detectors that we're trying to at Hanford and Livingston, we should get a binary black hole merger every 2 weeks, and sort of 1 to 10 binary neutron stars in the entire year-long run. It's really hard to say because that's an uncertain rate estimate. And there's lots of transients we'll be following up. We could get something new. You could get a galactic supernova. You could get something that was unexpected. And in that phase, we'll put out open public alerts for all binary black hole mergers and all binary neutron star mergers. So literally, a good amateur astronomer with a good quality telescope could have pointed to NGC 4993 and seen that, that remnant, that fireball on the edge of the galaxy as 2 neutron stars. And so someday that'll happen. I think it will probably be professionals for a while. But open public alerts in 03. That's it. Thank you.
We have time for a few questions.
Yeah.
Those catalogs that you had up earlier, are those available on the LIGO website?
Yeah. So if you go to LIGO.org, you'll find a news release for the catalog paper. And what it's doing, it will link you to 2 different places, actually. It'll link you to the archive article, and it will also link you to our DCC, which has an identical copy there. And once the PRX is published, assuming it's published, we'll get that up as well. Yeah.
Initial measurements on the expansion of space, so high, little, low?
Oh, so yeah, good question. So what happens is that because it's just a single event, we have a posterior PDF from which we can extract the value. But that's very broad, and it encompasses, it's basically 70. It's identical to the rough estimates that come out of cosmic microwave background searches, and supernova searches. But for precision measurement, like they're doing, there's already tension in those measurements. So it may be that they resolve that, right? We don't know who's right. If we get enough binary neutron star events, you may be able to side with one or select out some different parameter space. But right now, it's too broad to say. I'm sorry, I should have had that plot in here in the follow-up slides. I don't think I have it. But yeah.
With all the work you have to do to get rid of the environmental effects, does creating detectors on your surface help or hurt compared to low Earth orbit?
Well, the proposal for space-based detectors is for a Lagrange point in a solar orbit, right, trailing the Earth at 60 degrees. That's the nominal configuration for the 3-satellite LISA configuration. LISA's an ESA project that NASA has recently rejoined after going out after 2007. And that's expected to fly in 2030. So that probably will be about $2 billion. You're absolutely right. It's great to have it's great to have it in space where it's got a good quality vacuum. You don't have to make your vacuum. There's no environmental couplings. But nonetheless, it's probably its price tag somewhere above $1 billion. And so the funding profile for NASA didn't fit LISA, a joint NASA-ESA project in 2007, 2008. But now, after ESA did this Pathfinder mission in December 2015, in which they flew in a low Earth orbit, they did a proof of concept for the drag-free technology in which you have a satellite that houses, 2 test masses and some interferometry on board to say where they are relative to that satellite, and the satellite servos around it to protect it from solar wind and so forth. And the noise properties of that interferometer worked at the design level for not just for the Pathfinder mission, for the actual LISA space-based detector. So that was a hugely good result. And you also had the ground-based detection that meant people were comfortable with the propagation of gravitational waves and leakage into somewhere else, other dimensions, or whatever people proposed by which you couldn't measure gravitational waves. People occasionally said this. So I think that those two things mean that there's a lot of momentum for LISA to fly. So it's a great experiment. It'll be one of the great observatories when it does.
Other questions? So I want to remind you that the department is hosting a reception for Mike, and an opportunity to meet with him, ask him any additional questions, have some nice conversations, adult beverage of your choice. And that's right out here, right after we're done. And with that, let's please thank our speaker again.